This tutorial will look at the assignment of velocities to atoms and some facets of the velocity dialog box, particularly including the quenching of rotation. First of all, we'll get a molecule. We'll do something very simple here. This is a fluorine diatomic molecule, F2, lined along the x-axis, or along the y-axis here. Coordinates are, let's put it at the origin. Let's move it over to the origin. And now this is at plus 0.71, and this is at minus 0.71. Let's optimize this. We're going to use molecular mechanics MM+, and let's optimize this structure to make sure we're sort of where we're starting. No internal energy. So here's our molecule. Now what we're going to do is make this molecule rotate. So what we're going to do is take and assign velocities, a velocity here in this direction along the positive x-axis and a velocity for this atom along the negative x-axis, and that will cause the molecule to rotate around the z-axis. When we assign velocities, we can either assign velocities all at once to a set of atoms, either to a selected set or to the whole set. If we don't have anything selected, then the velocities will be applied to every atom. In this particular case, we're going to select atoms. We go up and we say set velocity. This dialog box tells you what the current velocities are, as well as allows you to set velocities. So the current velocity is 0 here for everything at this moment. What we're going to do is set some velocities, and we're going to make this one go 5 angstroms per picosecond, some number like that, and we'll have it along the positive x-axis. So and we'll have to check this box. If we want these new values to be taken, we have to set this checkbox here. So now we're assigning a velocity to that particular atom along the positive x-axis of 5 angstroms per picosecond. So this is assigned. We take this one now and we go up and set its velocity to be the same magnitude but in the minus x direction. And so now we've assigned the velocities to these two atoms, and we have velocities for the whole system. If we go up and have nothing selected and look at this, we'll see the velocities for the whole system. What we see is that the center of mass velocity is 0, so the molecule is not translating. The translational energy is 0 because we haven't got any translational motion. We could have assigned velocities that gave translational motion, but the velocities we assigned gave us rotational motion. So this is the rotational energy, 1.1 kilocalories, and this is the angular velocity of 6.9 radians per picosecond. And this angular velocity is directed along the negative z-axis, or it's rotating about the z-axis as we have told it to do, or given it velocities that would rotate about the z-axis. So now, if we want this thing to rotate, we have velocities. In order to rotate, we have to tell it to do molecular dynamics and to do restart. Restart doesn't equilibrate the velocities or anything like we would do without this checked. And with this checked, it means to start the trajectory with the existing velocities, to restart the trajectory, or to continue with the current velocities. So if we do this, and let's run for a little bit longer than this. Let's do it to say 0.3 picoseconds at this. I think that's something like that will be appropriate, and we just tell it to go, and what we see is the molecule rotating about the z-axis. That's because we gave it rotational energy only, no translational, no vibrational or anything, because we had optimized the structure. The only thing it does is to rotate. So that was the 0.3 picoseconds of rotation. If we go up and look at the velocities, again, there's no translation. We still have this rotation going on, 1.13 kilocalories of rotational energy, and what I'm going to do now is quench that rotation. and tell it to eliminate the rotation. We generally might like to do this with a very big molecule like a protein or something. If it's all the time the trajectory is going into rotation, when we want to go into internal vibrations and stuff, we can basically just quench all rotation of a molecule, and that's what we're going to do here. When we do that, if we turn on molecular dynamics again and do a restart, we'll see that it doesn't rotate, doesn't move at all, basically, because we have quenched all the rotation. So there is basically no movement of this molecule. And if we look at the velocities, the angular velocity is now 0 or been quenched, and the rotational energy is 0, and we have quenched the rotation. Similarly, we can quench the translation if we like, but this tutorial then gives you a little idea about some of the facets of how you set and investigate velocities using this dialog box.